Welcome students. In the last video, we have discussed about the basics of op-amp and the ideal and practical properties of op-amp. In today's video, we are going to discuss about the inverting op-amp and the concept of virtual ground along with it. Now, in op-amp, the input and output properties has a linear relationship between them. Now, in open loop conditions, this linear range is very small. Hence, the op-amp cannot be used as an amplifier. To use the op-amp as an amplifier, its gain must be controlled, and this property can be satisfied by using a feedback connection. The feedback connection is when the output is fed into the input signal, and the feedback of op-amp is classified into two types, that is positive feedback and negative feedback. Now, let us draw the circuit. Here are the two terminals, that is the positive terminal and the negative terminal, and this is the output of op-amp, and let us name it V0. When we are connecting this output into the positive terminal, this condition is called positive feedback of op-amp, and when we are connecting this output into the negative terminal, we are calling it the negative feedback condition. In the positive feedback condition, the fraction of output is getting directly fed to the non-inverting terminal, and it is added to the non-inverting input, and this leads to the instability of the system. In the negative terminal, in the negative feedback condition, we are applying it to the inverting input, and this can be done by three types. That is, if we connect the positive terminal to an input source, and by connecting the negative terminal to ground. Also, we can provide the input to the negative terminal and connect the positive terminal to ground. And in third condition, we can connect both the inputs to a common voltage source. Let us discuss the circuit of inverting op-amp. Here, let us take the two terminals and let V0 is the output. Here, the positive terminal is grounded and the negative terminal is connected to the voltage input source V. A feedback resistor is connected from the output to the input line. Now, let us name the feedback resistor as RF, and let us name this resistor as R1. Let I1 amount of current passes through it, and let IF current passes through the feedback resistor IF. Now, let us come back to the concept of virtual ground. Now, as we have said, this virtual ground condition is applicable for the negative feedback condition. In the negative feedback condition, we can say the open loop gain, let us denote it AON, the open loop gain is limited to 10 to the power 5 to 10 to the power 6. We have discussed this property in last class. Now, as we know, the output signal is given by V0 equal to A times VD, where A is the gain and VD is the differential input. Now, if we put V0 equal to, in place of A, let us put 10 to the power 6 multiplied by VD. Now, this VD differential voltage will be equal to, if the V0 is 1 volt divided by 10 to the power 6, or we get 10 microvolt. That is, the differential voltage will be 10 microvolt if we obtain the output of 1 volt. Now, this 10 microvolt is a very small and negligible quantity, and hence we can say that the voltage at positive terminal is equal to voltage at negative terminal. And in this condition, we can say that the positive terminal is grounded, but the negative terminal will be equal to 0 volt. Still then, it is not grounded, and hence this condition is called the virtual ground condition. We have to derive the expression for output voltage for the inverting op-amp. In this case, the signal at the positive terminal is equal to 0 because the terminal is grounded, and also the signal at negative terminal is equal to 0 because this signal acts like the virtual ground condition as we have discussed earlier. Now, let us name this point of intersection as X. We can write according to Kirchhoff's laws that I1 equal to I plus IF. Correct? Since the input impedance of an ideal op-amp is equal to infinite, then the value of I through the op-amp will be equal to 0, and hence we can write I1 equal to IF. Now, putting the respective values for the signals, the I1 can be written as Vx minus V input divided by the resistor connected R1. And similarly, the IF can be written as V0 minus Vx divided by the resistor connected RF. Let us name it equation number 1. Since from the virtual ground connection we get the V negative terminal 0, the V negative terminal as 0, we can write the Vx is also equal to 0. Now, using this value in equation 1, we can write minus V input by R1 equal to Vx divided by Rf. Now, this expression can be written as V0 by V input equal to minus Rf by R1, and this gives the open loop gain, the closed loop gain of the op-amp. The negative sign in this case indicates that the output obtained is in opposite phase of the op-amp, opposite phase of the input signal. Hence, from this we can conclude that even if the values of V output and V input are kept constant, the gain can be controlled only by using the values of Rf and R1. Now, for a special case, if Rf will be equal to R1, if Rf will be equal to R1, we get V0 by V input equal to minus 1. Let us write that V0 by V input equal to minus 1, or we can get V input equal to minus V0. From this we can conclude that if the values of Rf and R1 are equal, then the output signal will have the same magnitude as the input signal, but it is provided with a negative sign, which indicates that the phase of the op-amp or the phase of the signal is alternated. That is 180 degree phase with the input signal. Now, in this condition, we can conclude that the op-amp's gain depends upon the values of Rf and R1. We have discussed about the inverting op-amp, the conditions for virtual ground, and the expression for the closed loop gain of the inverting op-amp. Thank you for watching the video.